Hello everyone. It's a pleasure to be here with all of you today. Let me introduce myself. I'm María Fernanda Montero, and I am a member of the project Plasmas de Interés en Astronomía y Geofísica. I will show you the topics that my group and I are working on, and I have my talk in 5 parts. Let's go. Plasmas of Interest in Astronomy and Geophysics. Project Director Patricia Sayago, members Omar Benvenuto, Dario Berecín, Alejandra De Vito, Claudio Giordano, and María Fernanda Montero. Firstly, I'd like to tell you about accretion disk and binary systems. Accretion disks are important at different scales in the physics of the universe. For instance, binary system called redback, closed binary system composed of a normal giant star and a neutron star, have shown transition from an X-ray emission state to radio pulsar state. This transition might be connected to instabilities in the accretion disks. In the X-ray emission state, the neutron star is accreting material. In the radio pulsar state, the millisecond pulsar is observed. We show our first study of local instability in the disk due to a magnetic field and its influence in the viscosity. We analyze the increment of magnetic field by dynamo process, taking account the characteristic time scale of Parker instability, magnetic reconnection, and magneto-rotational instability. These are the equations that describe the problem. These are the equations that describe a dimensional magnetic field. And this is the coefficient of Sakura-Tsunev. Here appears the dependence of magnetic field. This chart describes the variation of a dimensional magnetic field as a function of the adimensional time. The last one shows the viscosity as function of the adimensional radius, kinematic, effective, and the difference between them. Secondly, I'd like to talk about Magnetohydrodynamic model of circumstellar envelopes in early type stars. From the increasingly precise observation obtained with large interferometers, the evolution of the star model is fundamental. Although the formation of a disk that would explain some aspect of the characteristic spectrum of this object is accepted, some points are not so clear, which means that other models might adjust the same observation. In this work, we present the first result of a two-dimensional magnetohydrodynamic model that describes both the circumstellar envelope and the wind coming from the region near the poles. The problem is described by these equations. Here, the formalism of a stream function can be used. This formalism is applicable to the problems with an ignorable coordinate. The symmetry allows the ideal magnetohydrodynamics MHD equations to be reduced to a single differential equation, eventually another equation, for both static equilibrium and stationary flows. The first figure shows the magnetic induction field lines for the magnetostatic problem. Numerically solving the equation for the function phi and replacing in the expression of the particle density, the figure on the right is obtained. These are the lines of constant density. We can see that it doesn't look like a disk. Thirdly, I'd like to describe the topic analytical study of different terms of Ohm's generalized law on the stability of magnetic flux tube and the modification of wave propagation. A conducting source moving uniformly through a magnetized plasma generates among a variety of perturbations and then waves. They propagate in a variety of plasmas under many kinds of conditions. Like the electromagnetic radiation wheels up Cherenkov cones, alpine waves can wheel up structures in the plasma called alpine winds. Alpine waves and winds have been detected and measured in many solar system bodies, and their existence has also been theoretically proved. For example, they are detected and measured near the Galilean moons, moving in the Jovian ionosphere (MHD), and near asteroids such as Ida and Gaspra, moving in the solar wind (HMHD). Under certain conditions, whole thermal electronic pressure must be taken into account in the Ohm law, and so on gets whole magnetohydrodynamics (HMHD). Some years ago, Sayago and Placek have shown the existence of alpine winds in HMHD. Recently, Sayago has analyzed the stability of an alpine wind in the presence of an incompressible perturbation that has the same symmetry as the structure and polarization in HMHD using analytical method. An analytical method for the study of the stability of a static structure with a symmetry in magnet-side plasmas in the presence of incompressible perturbation with the same symmetry as the structure was developed by Palumbo. Since alpine winds are a stationary structure, Sayago and Placek have shown the stability of such alpine winds in MHD conditions by extending Palumbo's method. As mentioned before, this method has also been extended for alpine winds in HMHD conditions. Sayago concludes that, in the presence of this kind of perturbation, alpine winds in HMHD are stable. Fourthly, we'll move on to the next topic: magnetic reconnection and terrestrial auroral region analysis of different coupling functions solar wind terrestrial magnetic field. Magnetic reconnection takes place when two plasmas whose structures are topologically different meet. It is a diffusive process that allows the extraction of magnetic energy from the plasma, transforming it into kinetic energy of the particles that enter the magnetosphere. In the case of magnetic substorm, this phenomenon takes place in the auroral region and can be recorded both in a station on the Earth's surface and in satellite observations. For example, Advanced Composition Explorer satellite. The main objective of this work is to analyze geomagnetic substorm and their relationship with disturbance in the interplanetary magnetic field. This analysis has been carried out by studying the coupling functions. These functions estimate, based on satellite data, the amount of magnetic energy from the solar wind that can be transferred to the magnetosphere through magnetic reconnection. About 1 to 2 hours after the value of the coupling function exceeds a particular threshold, the energy needed to develop a substorm enters the magnetosphere. In order to verify these events, data from ground magnetic stations of the intermagnet network were used. We have compared our set of substorms with numerical simulation published in 2019 by Ebihara, validating their model. Therefore, confirming the relationship between the minimum SML index and the physical parameters of the solar wind. Finally, I'd like to tell you about space plasmas under Hamiltonian Formalism. There are many problems in physics and applied science where transport plays an important role. Some examples include the magnetic confinement of fusion plasmas and vorticity mixing in fluids, among others. As you can see in this picture, we can observe the different structure in the flow, like vortex and vortex streets. Both plasmas and physical flows are typically found in turbulent state. However, in two-dimensional systems, the turbulent state usually contains large-scale coherent structures like zonal flows and vortices. Accordingly, a realistic transport model should include both elements, the stochastic component of turbulence and the deterministic component of large-scale coherent structures. On assuming that the flows are two-dimensional and incompressible, the equations of motion of test particles are Hamiltonian. One of our goals is to use the analogy with Hamiltonian system and apply dynamical system ideas to study transport. In particular, the referred transport problems are closely related to important dynamical system problems, including the transition to chaos in non-twist systems for which the Cam theorem cannot be applied, as well as the study of anomalous diffusion and Levy statistics. A few years ago, a non-autonomous version of the standard map was introduced by Calleja in order to study these phenomena. In this project, the transport phenomena will be addressed by a linear stability analysis. The flows under study will be dominated by large-scale coherent structures, such as zonal flow and vortices, which will be modeled by Hamiltonian systems exhibiting chaotic transport. These ideas will be applied to the study of turbulence in magnetic reconnection. Thank you for your attention.